Hi, everyone. Welcome to this week's seminar. We're excited to have Dr. Greg Dusek from the NOAA National Ocean Service giving the seminar. He received his PhD in physical oceanography from the University of North Carolina, and he's now the Chief Scientist for the National Ocean Service Center for Operational Oceanographic Products and Services. And his research focuses on coastal oceanographic product development through the intersection of data science with coastal hazards. So welcome and look forward to your talk.
All right, thank you. And thank you everyone for joining me, and thanks for having me. It's great to be here. Had a great day today at UNH. And so I'm going to be talking about rip currents, and particularly rip current forecasting and communication at NOAA. And we've had a lot of progress with RIPS over the past decade or so. And I'm going to kind of walk through that progress and kind of point to where we're going in the future. But I wanted to start with a, with a story about Dustin Fletcher, who was a 28-year-old retired boxer who was swimming off the coast of New Jersey about 2 years ago on September 22nd of 2017. And he was swimming there while Hurricane Jose was churning offshore. And although Hurricane Jose didn't have any direct impacts on the coast, it did generate large waves. And usually when you have large waves, you're going to have strong rip currents. And in September in New Jersey, you also don't have lifeguards on the beach because a lot of lifeguards have gone home for the year. And so Dustin's swimming by himself in the beach, and all of a sudden he finds himself caught in a rip current. And the article, he goes on to say that before I knew it, I was 30 yards out at least. I kept trying to swim in, but the waves were so choppy. I started to feel helpless. I started to panic a little. I was getting tired and felt myself breathing really fast. I was totally helpless. I thought I was going to die. And this is a pretty athletic guy, obviously, presumably a decent swimmer. And luckily for him, though, there was someone around, as you can see from the headline there, a bystander, and they rescued him, and so he didn't die that day. And in this case, bystander rescue is typically what we tell people not to try to do, because often people who go in to try to make a rescue can be the ones who die. But in this case, they both made it out okay. Now, later in the article, Dustin goes on to say that he actually knew he was caught in a rip current. He knew he was supposed to try to stay calm. He knew he was supposed to try to swim parallel out of the current and back to shore, but he couldn't do it. And if it weren't for that person, he might have died that day. And so he knew what he was supposed to do, knew about rips, but he still had this problem. And one of the reasons he might have known about rip currents and what to do is the Break the Grip of the Rip program. And so if you've been to the beach, you might have seen this sign. How many people have seen this sign before, out of curiosity? So about half of you, maybe. These are at public beaches up and down the East Coast and across the US. And this is a program that started at NOAA in 2004 or so. And the idea was to try to increase awareness about rip currents and what you're supposed to do if you're caught in a rip. We've done some recent social science work I'm going to talk about a little bit later, which suggests that the program has been pretty successful. In one national survey, 91% of those surveyed were aware of what rip currents were and generally what to do if caught in one. In a North Carolina-based survey, 85% of those surveyed knew common advice of what to do if caught in a rip current. So there's some evidence suggesting from these surveys and from anecdotal evidence like Dustin's case that people are more aware about rips and what to do if they're caught in these hazardous situations. And so it seems to have successfully increased awareness in what to do if caught in a rip. However, we're still seeing lots of rip current drownings. So NOAA records drownings of rip currents every year in the US. And you can see here, 2016, 17, 18, nearly 70-ish drownings related to rips in the US each year. 55 so far this year. That's preliminary. We still have a couple months left. That number will probably get closer to 70 as well. And the actual number of drownings is probably quite a bit higher. There's estimates, some recent work done showing that it's probably more like 100 per year, but many don't go recorded as rip currents or go recorded as other types of drownings. And so maybe about 100 rip current drownings per year. So even though our messaging seems to be working, clearly there's still a significant hazard here and people are drowning. On top of that, USLA estimates that over 30,000 rip current rescues are made each year. And so the question here is, if our messaging so far has been somewhat successful, but we're still having these drownings, what else can we do? And so what NOAA has tried to look at is how can we improve preparedness and prevention? In other words, what information can we give to people so that they don't get themselves in this potentially life-threatening situation in the first place? Because that's how we can really hopefully reduce the number of drownings and rescues. And so before I get into some of our forecasting and communication work, I wanted to start with just some basic definitions. First, what is a rip current? Kind of the textbook definition is a relatively narrow offshore directed jets of water that begin in the surf zone. I think this video shows it a little bit better. This is drone footage we captured on the Outer Banks of North Carolina near Kill Devil Hills. And you can see the rip right there in the center of the image where you have foam being transported offshore. That's one way you can identify rips, sometimes with sediment-laden or discolored water. Also, you'll notice them where you kind of see a lack of waves breaking, where there aren't waves breaking. You see waves breaking on either side and less waves breaking where there's a rip. In terms of characteristics, typical rip current anywhere from about 100 to 400 meters long, 15 to 100 meters wide. And they can last anywhere from minutes to months, really depending on the type of rip. Some of them are over very quickly. Some of them can be semi-permanent. And then in terms of speeds, velocities of about 2 meters per second, which is about 5 miles per hour in terms of the maximum velocities. And that sounds kind of slow to most people. But if you consider that when Michael Phelps set his world record in the 100-meter butterfly about 10 years ago, he averaged about 2 meters per second. So unless you're an Olympic swimmer, that's pretty fast. And just a note, I found out Michael Phelps no longer holds that world record, but I'm still going to use this picture because he's the most famous American swimmer, I think. In terms of why rip currents occur, here's that same rip. We put dye in it a little bit higher up. And you recall that I mentioned that on either side of the rip, you tend to see increased waves breaking. And the reason is because there's a sandbar there or shallower water. And where there's the rip current, there's a channel or deeper water. And so you get an increase in waves breaking over the sandbar and a decrease in waves breaking over the channel. And that's important because where you have breaking waves at the beach, you have something called setup, which is a relative increase in water level due to breaking waves. And that setup is directly related to the height of breaking waves. So where you have larger waves breaking and increased breaking activity, you have higher setup. Where you have smaller waves or a decrease in wave breaking, you have lower setup. And water wants to flow downhill, so it flows from regions of high setup to low and offshore through the rip channel. So that's kind of your classic bathymetry-driven rip current, driven by the shape of the bottom. You can also have rips caused by purely hydrodynamics. Waves coming from different angles can cause similar gradients in wave height like you see here. You can have rips caused by structures like jetties or piers. But in our case, at least for our forecasting thus far, we've really focused on this type of rip, in particular, a bathymetry-driven rip, because these tend to be the most common in terms of hazard on open beaches in the US. So with our forecasting work, we started this about a decade ago, actually when I was in grad school at UNC, on the Outer Banks of North Carolina in Kill Devil Hills. And what we were trying to determine in part was, can we accurately forecast rip currents? Up to this point, NOAA had done some work trying to predict rip currents using a very simplistic kind of spreadsheet index-based approach. It wasn't forward-looking at all, and as I mentioned, it was very simple, and we thought we could do better. And so we went out, we collected information about the shape of the bottom, the sandbar using GPS, like you'd see there on the left. We deployed some Doppler current profilers to measure the waves, you can see there in the middle, and then we worked with the local lifeguards to collect observations of rip currents, because obviously to determine if you are going to have rips or not, you need to know if they're there. And rips are really hard to observe in situ because it's hard to put instruments in the surf zone, right? They can get covered by sediment, get beaten up by waves. And at the time, there wasn't all too much done in terms of camera work. And so what we worked with the lifeguards, and they had their data record of rip current rescues. They knew when and where people were rescued from rips, and they observed on the beach a group of 18 lifeguards every day when they saw hazardous rips, twice a day. And so we were able to use that information to create a rip current forecast model. And this forecast model is a statistical model relying on a number of inputs to predict rip current likelihood: significant wave height, wave direction, water level, or mostly due to the tide, and a post-wave event variable, which is effectively a proxy for the bathymetry I'll talk about here in a second. And they go into a logistic regression model, a statistical model, and the outputs the likelihood of a hazardous rip current occurring between 0 and 1, or 0 to 100%, not dissimilar to what you see in a precipitation forecast, right? A likelihood forecast. To give you an idea, and just to say, when we first installed this in Kill Devil Hills, we found a 67% improvement compared to the index approach I mentioned before that most weather service offices were using at the time. To give you an idea of what the forecast model looks like, this is the output, and the color scales to likelihood, so blue low likelihood, red high likelihood. On the vertical axis is water level or tide, significant wave height there on the bottom left, and mean wave direction on the bottom right. And you can see as you increase significant wave height, you generally see an increase in likelihood, not surprising, right? Larger waves lead to stronger rips. But what I want to draw your attention to is right around about 0.7 meters or so wave height, a little over 2-foot waves, not very big. You can see at mid-tide level, you get a pretty steep increase in rip current likelihood over a small range of wave heights. So in other words, you can have waves that don't look too big, that might not look hazardous to the average person, but can cause a hazard. And that's when we see a lot of our rescues and drownings, when the waves aren't too big, but big enough to drive strong rips. With wave direction, as you increase wave direction, you see a decrease in likelihood. And that's due in part due, if you think about waves coming in at an angle, they tend to drive a stronger longshore current, and that can suppress rip current activity. And then in terms of the tide, you'll notice for similar height and direction conditions, at low tide, you tend to have stronger rips. And that's because at low tide, you have more wave action breaking over the sandbar, driving that circulation I mentioned before. Whereas you could have the same situation in wave height, but then at high tide, all the waves don't break on the bar. It's deep enough that they break right on shore. And you can basically erase that variability that I mentioned before in terms of longshore variations in breaking wave height. And so the tide can be really important when looking at rip current likelihood. So this was our model. And as I mentioned, it worked pretty well. And then one more thing, the post-wave event variable I mentioned. So that, as I mentioned, rips are very dependent on bathymetry. And so if you have a large sandbar, that's pretty important to know, but it's really important to observe. And so what we ended up finding is following wave events, about 3 days or so following a moderate wave event, you generally see a more substantial sandbar and an increase in rip activity than if you weren't following one of those events. And so for our wave variable, it's just a 0 or 1. Are we following one of these wave events or not? Which somewhat accounts for bathymetry, but as I mentioned, quite simplistic, something we need to improve on moving forward. So we have this forecast model, but what we need to actually be able to project the likelihood into the future is wave and water level model to drive this statistical rip current model. And that's what we have now in the nearshore wave prediction system. So this is an operational wave and water level model run at all weather service coastal WFOs throughout the US. And you can see the coverage there. It provides inputs along the 5-meter depth contour, which is basically the approximation for where waves are going to be breaking. So gives us as close as we can to breaking wave height. And it provides forecasts about every kilometer along shore, every hour out to 6 days into the future. And so with this, we can have a fairly extensive rip current forecast that we can provide to the public. You can actually see this output right now at the website there as well. It's online. And so right now, our rip current forecast model is running experimentally at 20 different weather forecast offices across the US. It's hard to see here, but I'll zoom into North Carolina to give you an example of what it looks like. You can see every one of those data points is about a kilometer or so apart. The color indicates the likelihood over the next couple of days. Gray if it's going to be very low, yellow moderate, and red high. And if I click on one of these time periods in one of the points, it brings up the 6-day forecast for that location. And so in that plot, that's time series plot, you can see on the top is the rip current probability or likelihood. The next plot down is significant wave height, wave period, wave direction, and then the tide or the water level. And you can see how, over the course of a few days, that water level variability is very evident in the signal. And then it's obviously very dependent on wave height. So larger waves, you tend to see larger rip currents. And so this is right now being tested, and I'm going to talk about that a little bit. It'll be operational by next beach season, and including in New Hampshire beaches. So if you go to the beach, you're going to see output from this next year. So we have this model. It's been well validated in North Carolina, but we obviously need to validate it in other locations and in other cases. And so a series of validation efforts are underway or have occurred and are underway. One was an in situ validation where we did most of this work using lifeguard observations, visual observations of rips. But are those a good proxy for actual rip current intensity or speed? So I'm going to show a little bit about that. We've done additional lifeguard observations at other beaches across the US. And then moving forward, we're looking at doing some webcam observations in place of lifeguards. I'll talk about that a little bit as well. So in terms of our in situ observations, this was work done with Melissa Moulton from University of Washington, Britt Robenheimer, and Steve Elger from Woods Hole. They collected in situ obs of rip current speed, which I mentioned before are really hard to collect. But we have some for 2 periods, one in 2012 and one in 2013, using current meters or current profilers. And in 2012, they actually generated their own channels in the bathymetry using an amphibious vehicle, which you can see there in the bottom right. So they drove that through the surf zone to create rip channels and make sure that they had rips. In 2013, they just used the surf zone bathymetry as it was to be able to observe some rips. So we used that data and compared the speeds that were observed to what our forecast model said. And so here's an example of the comparison. On the top, on the left, is the observed rip current speed from 0 to 1 meters per second. On the right in blue is the likelihood from 0 to 1. And then wave height, wave direction, and tidal elevation or water level. And so you can see just qualitatively that the likelihood forecast agrees pretty well with the observed rip current speed. Especially during those 2 periods of kind of elevated speed, we see pretty high likelihoods. And then in the low period there, not very likelihood of strong rips, borderline hazard probably, but you can see that the model captures the tidal variability in the phase really well. And so qualitatively, we were very happy with this comparison. But the likelihood is not really a direct measure of speed. What it's really saying is a yes or no. Do I have a hazardous rip current or not? So the question is then, what is a hazardous rip current? How fast does a rip current have to move to be hazardous? And so to answer that question, we looked at the observed speeds and looked at different thresholds and compared those thresholds to see, where should the yes/no line be? What speed? And when we used a threshold of about 0.2 meters per second, which is really not that fast, we found that the model compared most favorably with the observed speeds. And we got something called the Breyer skill score greater than 0.6. And what the Breyer skill score is it just allows you to relate the skill of the model to a climatology, usually just the climatological mean at predicting the hazardous rip. In this case, 0.6 means a 60% improvement in using the model over the climatology, which is a really good result. And then if you take this 0.2 meter per second speed and show it on a reliability diagram, you see that the forecast is pretty consistent regardless of what the forecasted probability is. So that's on the right here. And so what a reliability diagram enables you to do is compare the forecasted probability to the observed frequency of the event. In other words, for example, if you have a forecast of 0.6, on 0.6 likelihood to have a hazardous rip, given these conditions, you would expect that you would see a hazardous rip 60% of the time. If you see it more than that, in this case closer to 0.8, that means that you're under forecasting the conditions. So if you're on that side of the black line, you're under forecasting, you're not forecasting hazardous rips enough. If you're on the other side of the black line, you're over forecasting. So it gives you an idea of if your model has any inherent biases in different values. And in this case, you can see we're very close to the 1-to-1 line, which is the dashed black line in the middle there. And so we're performing pretty well. And so this was a pretty interesting result. And I think one of the important parts about this, in my mind, was that it shows that rip currents as slow as maybe 0.2 meters per second could be hazardous, which is a pretty slow speed. I mean, that's not moving very fast. You remember I mentioned before, rips can get up around 1 or 2 meters per second. So I think that shows that you don't need water moving that fast to potentially cause people problems. So that was kind of our in situ validation. We also looked at rips at a number of different coastal locations compared to lifeguard observations, including Boston, New York, Maryland, Virginia, North Carolina, Miami, Tampa, and San Diego. And I'm just going to give you a couple examples of these results so far. And so these are using lifeguard observations On the left here is Maryland down to North Carolina. On the right is Miami. And in both these cases, the lifeguard observations were once a day, just the strongest rips that the lifeguards observed compared to our forecast model, which isn't ideal because we're not capturing that time variability, but lifeguards are on the beach to do more than just collect us data. So we'll take what we can get. And you can see these are the same type of reliability diagrams I just mentioned before. And in both cases, they're not terribly biased. They're under forecasting a little bit. That's maybe to be expected because in both cases, this is using the equation that was calibrated at North Carolina. And so dynamics are going to be a little bit different depending on where you go. So in theory, we should have to recalibrate our statistical equation in different locations, which we haven't done yet. But in this case, both cases showed a 22% improvement over the climatology at predicting hazardous rips. And at Miami, we found a 30% improvement over the existing index approach that I mentioned that the Weather Service uses. So we're pretty happy with these performance at both of these locations, but we really want to investigate, what happens if we calibrate at a specific location? Can we do better? The challenge with that is we need good observations to calibrate the model too. And for an example for that, I'll give you San Diego, where the lifeguards there have been recording twice a day rip current observations at specific times for an extended period of time. So we feel really good about the lifeguard observations there. And you can see if we apply the original calibration in North Carolina here, we get a substantial over forecast in the likelihood of hazardous rips. And this period here was from November 2017 to April 2018. And so what we ended up doing is this is kind of the cold months. And we found that there was kind of a distinction between the forecast capability between the summer months or the warm months in San Diego and the cold months. If we calibrate to the lifeguard obs here, you can see that we get a very good performance in terms of the bias. We get a good, reliable forecast across all probabilities. And in terms of improvement over the existing index approach, when we calibrate this model for San Diego, we see in the cool season, which is shown here, we got a 16% improvement over what they're providing now. And in the warm season, we see a 32% improvement. And I'm not showing the warm for this particular case. And so, so for San Diego, we're pretty happy that when we calibrate it in another place that the model's going to perform well, which is important because when we first did this, we really didn't know, is it going to hold up if we take it to a place that has wildly different wave characteristics, tide characteristics, but it does seem to do pretty well. So the last part with validation is getting into cameras. So lifeguards are great, but obviously you have potential questions. Does a lifeguard in one place see a rip current like a lifeguard somewhere else? So if you don't see a good agreement with what the lifeguards are seeing, is it because the model's not doing well, or is it because those lifeguards are just doing something different? So there's a lot of qualitative components to just visual observations. And so what we're starting to move to is using webcams to observe rips. And so we set up this, what we call a webcam application test bed in the southeast of the US at 7 different locations. And this is a partnership with a whole bunch of people, including Surfline, the webcam company. And we have these cameras installed. They've been installed for over a year now, almost 2 years in some places. And we capture 10-minute video chunks at all these, every 10 minutes we have a video chunk at all these different cams. And we can use that data not just for rips, for a whole host of things, including observing mammals, observing people on the beach, wave run-up, a lot of different things, but also helpful potentially for our rip current validation. And if you look at the Miami cam, which looks pretty nice right now, you can see in this particular case, you remember before I said, where you have waves breaking, you can see the bar. And then where you don't have waves breaking, you have deeper water, you can see a channel. And so one very simplistic way to see if you have rips or not is just to look at a time average of a video for 10 minutes and see where your waves are breaking and where they aren't. And it gives some indication of the bathymetry and if you might have rips. And so this video here is an example of some of those 10-minute averages. So every hour, we have a 10-minute average of video, and you can see where waves are breaking and where they're not. And on the bottom here is the rip current likelihood from 0 to 100. As I play through this movie, what is our forecasted likelihood? How does that compare to what we see in terms of the video? And I'm going to play this, stop it quickly. And you can see here how you have those darker areas where you have waves breaking and kind of the muddy, they look muddy in this case because the water is very, very shallow. And then you have channels there where you can see you potentially have rips. And so I'll play this through and just qualitatively, you can kind of see how the forecasted likelihood increases when you see those increase in wave breaking, and when you kind of see less waves breaking, you have a lower likelihood. And so this is kind of just the first cut effort at kind of looking at these two things side by side. We have a graduate student that was working on actually putting bounding boxes around all the rip currents that they would observe in the footage, and doing a more direct comparison both with what the lifeguards are seeing in Miami, and then also with what our model is saying. And that's a little bit of a work in progress. But I think this has kind of a qualitative potential to help us validate our forecast model. Also, in addition to this, we're working with a group at UC Santa Cruz to apply the observed rip currents to a machine learning approach, use a machine learning approach to apply to these bounding box of rips to try to identify rips using AI or using machine learning. So here's an example of rip detection using this machine learning approach from the footage that I showed you earlier. And what it's showing you is it's identifying, it's looking at each frame of the video and saying the likelihood that it sees a rip at that location for those videos. So this is showing some promise to be able to take something like this and apply it to all of our footage. We're also looking at potentially looking at flow characteristics. So actually analyzing the video, tracking particles and things like that, and trying to see if we can detect rip currents those ways. So that's a work in progress, but this has a potential to really improve how we're able to calibrate our model, improve our model moving forward. And so that's kind of where we stand right now with our rip current forecasting efforts. But obviously you could have the best forecast in the world, but if you don't communicate it well, it's probably not going to make much of a difference, right? And so one of the things we started about 4 years ago now is working on our social science efforts with coastal hazards, in particular rip currents. And so we had a workshop in 2015 where we met with a bunch of lifeguards, forecasters, academics, emergency managers, media members, a whole host of people to try to say, how can we improve communicating our forecast? Once we get this new forecast up and running, how can we make sure we're communicating it well? How do we visualize it? How do we message likelihood? And then how do we communicate, with communicating about rip currents in general, as I talked about in the beginning, is our break the grip of the rip effective? And how can we improve communicating prevention? Because that's kind of the piece we haven't really focused on so far. So coming out of this workshop, we did some social science work looking at our forecast. And so we created kind of a demo visualization of how our rip current forecast model might be visualized. This happened well before the previous page I showed you. So you can see we're already kind of following some of this a little bit. And we shared this with people and had them worked with the group to do a survey to try to see, do people understand what we're showing them in terms of forecasting likelihood? And we did this mostly in North Carolina. And this was the same public survey where we found that 85% of those surveyed knew common advice of what to do if caught in a rip current. So that was sinking in. And now this was a web survey, self-selected, so probably skews on the side of being a savvy beachgoer, let's say. If these numbers would probably be lower with the general public. But over 90% understood that what the product we were showing them was showing rip current likelihoods, not some other thing. So they seemed to understand the concept of likelihood, which was, I think, encouraging. And then on top of that, over 70% said they would stay out of the water for the highest likelihoods, which was, I think, a really important result because it says that people respect the forecast. So if we issue a forecast and NOAA is saying, hey, this is likely to be the case, people are listening to that, which I think is very encouraging. In terms of the visualization, we found that most people preferred just kind of stoplight colors and a very simplistic visualization. They didn't want to actually know what the likelihood value was. Like they didn't want to know it was 63% or something. They just wanted to know yes, no, kind of, or very simple whether they should be worried or not. We also had some expert focus groups of EMs and lifeguards, and they had similar results to the public survey. But one of the interesting parts of the focus groups I thought was we asked them the question of what does the public least understand about rips? And 63% said how to spot a rip, and 38% said how dangerous a rip can be. So both of them, again, this prevention idea that people don't know what to look for and they don't really know what the hazard might be in the first place. And so then that brings us to how do we improve communicating the hazard? So is this break the grip of the rip effort effective, and how can we improve communicating prevention? And so this was work where we did a national survey Again, a web survey, self-selected, so probably savvy users. About 91% knew about what to do if caught in a rip, and about 90% said that at least sometimes they will swim when there's not lifeguards, which is an important point because that's really when I think our forecast has value, where people are going to be in a situation where they need to make a determination for themselves if it's safe or not. So the forecast can help there, and understanding can I see a rip or not can help in those cases. So along those lines, as part of the survey, we had people look at images of rips and say, where would they swim? What's the safest part to swim in this image? So you can see the rip there with the red line. And so we'd give them the images. And what we found is that a lot of people, again, this is a savvy group on the left, they picked the right spot. They picked the place where there isn't the rip. The rest of the people picked the exact wrong spot, right in the rip. So, when people don't know what to look for, they see, hey, there's no waves breaking there. That looks calm. That looks safe. So people end up swimming in the place where we exactly don't want them to swim. And so about 54% thought that beach users could identify rips. So, a big chunk of people don't even think you can see them. And then about 54% only identified the safest place to swim. So in these images, about half the people picked the wrong place to swim. So these numbers are much more skewed compared to just 90% of people knowing about rips. Clearly, this is where we can make some progress in terms of hopefully giving people more information. And this inability to identify rips correlated with the frequency of beach attendance. In other words, people who don't go to the beach as much don't get these correct. And so, which doesn't surprise you, but those are often the people who end up getting themselves in trouble and drowning. And so the take home from the survey was that I think our Break the Grip of the Rip effort has been successful in the original goals. And then there's been evidence from the responses that signage and forecast can aid in prevention. In other words, people were looking at the signs and they're taking the forecast seriously. And the response suggests that there's interest in using the sign to learn about rip current identification. So in other words, a lot of people wanted to be able to identify a rip. They just weren't sure how to. So to that end, we created new rip current signage. And so you'll start seeing these signs probably at the beach pretty soon. And this was a work actually with some folks at Surf Life Saving Australia and some others. And the idea here, it's very similar to our existing signage, obviously. Some slight changes to the messaging to focus on staying calm and relaxing. Because panic is what tends to be the biggest issue with people drowning in rips. The other thing you'll notice is that we completely changed this color scheme to make it look more like a real rip. So in other words, dark, flat water where the rip is, and then kind of white water, breaking water on either side of the rip. And then we also highlight the person in the middle there waving as a means to say, hey, you can float. You don't have to necessarily try to swim. If you could stay above water, if there's someone there to rescue you, or in some cases, rip currents will actually bring you right back around to shallower water if you stay and float. And so, really trying to bring in some, it's subtle, but trying to bring in some of the things we saw in our social science to try to communicate better with our signage. In addition to that, we started a series of rip current safety videos. These went online, I think about 2 years ago. There's 4 of them, and ranging for different purposes. And they were really, again, relying on the most recent physical and social science. So all updated videos from what we learned in some of our surveys, and focusing again on prevention and not just what you do if you're caught in a rip. And these videos have had over 25 million views across all platforms, which is crazy. So we were really shocked at how these took off. I think these are the most viewed National Ocean Service videos ever. And so clearly, I think, again, this shows the public wants to know what to do. We just have to be able to get them the information. And then this past summer, we added a new new video to the series called Protect Yourself to Save Others. And it's a very short video. It's a little over a minute. You can find it on the web right now. The whole point with this was that we've been seeing so many cases where people rush in to save someone in a rip and they end up drowning. There was a number of those this summer. There was some, looking at the numbers in North Carolina, there's been some work showing that about 30% of all the rip current drownings over the past several years have been people going in to make the rescues, not the people who get themselves in trouble in the first place. So, and so what we're trying to do is just tell people to take 10 seconds to think about what you should do before you just go in after someone. And so that's, get a lifeguard is the best thing you can do. Get someone else on the beach, call 911. And if you try to throw them something that floats, if they're not too far away, if you have to go in the water, we tell them bring something that floats. And that's really the number one thing you can do, because if people go in with a flotation device, it could be a boogie board, it could even be a cooler, just anything that they're not going to sink, right? If they go in with that, they have a much, much, much greater chance of surviving, because, you know, as long as you stay above the water, eventually someone will rescue you. So this just rolled out at the end of last summer, and I think we're going to be making a greater push on this over the next several years. Lastly, I just want to touch on one last effort we have ongoing, and this is to use VR, or virtual reality, and to do this to assess what people are learning about RIPS, and then also hopefully communicate to people. And so we started this this past summer. It's kind of a simplistic VR, but the goal was to just get people in a RIP and see what they do, and start seeing if, you know, what are their reactions? How do they react to it? Because it might teach us more about how we can communicate to people. And so we put them in this VR environment, and they're in the ocean, in the coast. And we tell them to swim through buoys. So we show them that you can swim in VR. Then we have them wave to some people, so you can wave in VR. Then we let them loose. They swim around for a minute, and all of a sudden they start getting pulled from shore. And so then they have a set stamina, and we see what if they can get out of the RIP, or do they drown in this period of time. And so we did this summer with about 60 people or so at the beach in Long Island. And we haven't gone through all the numbers yet, but an initial look of our first survey participants showed that 51% or 51 of the people of 64 escaped by waving. So if you waved, someone would rescue you. 9 people escaped by swimming out, so you could swim parallel till you're out of the RIP and then get back to shore. And 4 people drowned. But what the interesting thing is that those 51 people that escaped by waving, a lot of them tried to swim first and were making no progress or whatever. A few people waved quickly, but a lot of them made an effort and then clearly just didn't know what to do or started panicking and knew that they could wave. And I was really surprised by this, because I thought a lot more people would swim out. And I think it shows that even in a VR environment, people start panicking. They don't know what to do. They're kind of starting to freak out. And I think that's what happens in real life. And then that's what leads to drowning. So we have a lot more to do with this in terms of studying, but I think this can give us a good insight in terms of how people react to hazard. And I think it can also help communicate, because you put someone in a VR environment and they have the potential to learn a lot more about something than just watching a normal video or looking at a picture or something. So I'm gonna finish up here, my summary. Again, rip currents are the greatest safety risk at the beach. Over 100 drownings estimated each year in the US. Our forecast model has demonstrated skill and is being implemented in operations. It'll be live next year. We have a lot to do still with making sure we're validating it everywhere and potentially improving it. And I think that's where really our camera efforts are gonna come into play, because I think that can really transform how we do this forecasting moving forward. The Break the Grip of the RIP program has been successful in what its initial goals were, but I think we're missing that focus on preparedness and prevention, which we're starting to transition to now. And then efforts are ongoing to include prevention in our messaging now in terms of signage, our videos, and potentially VR to try to assess what impacts our communication is having. And so I have some time for some questions, I believe. I just want to make sure to show these acknowledgements. You can see there's a whole lot of people on here, because a lot of people have contributed to this over the past decade or so. And really, without all this help from all these folks here, none of this work would happen. So thank you, and I'll take any questions.
So this goes to show my ignorance of AI, but when you send it the image, you're sending it the entire image, and it's also finding the rip current as well as the likelihood?
Yes.
Okay. I wasn't sure because the frame kept changing.
Yeah, so it's finding it in a slightly different location each time. Yeah, so you train it, basically you send it training images which have the boxes on them. And so it's object detection. So just like AI can detect people in a scene, it can really detect any object if you give it enough training data. And so that's what we're doing with RIPS. Yeah.
I was going to follow up with that one. Can those AIs actually detect a person in the RIP?
Potentially, yeah. Actually, I just heard some folks that I've worked with in Australia, Rob Brander, I don't know if you know Rob, his group, I guess, was starting to look at tracking people and seeing where they swim to see if where people are entering the water and stuff, I guess. So yeah, I think, and then I think potentially as a safety, awareness thing, if you don't have lifeguards on the beach, you could potentially be IDing people potentially getting in hazardous situations. So yeah, I think that intersection between people and the hazard,
Can I ask another question?
interesting.
I was curious, the constant level of drownings.
Yeah.
Is almost constant.
Yeah.
I even heard over the last 25 years, it's roughly been the same. Why is it the same if people were drowning at that rate before they knew what to do, after they knew what to do, and maybe even then there's more people, maybe there's more people in the water now, so they're relatively less number?
Right. Yeah, no, that is a great question. I wish we had better statistics because I'd like to know the answer to that. I think like you said, it's tough to constrain the drowning numbers. One, because we don't have a lot of faith in the numbers we have for drownings, just because they're not, they're better than they used to be. But, like I said, we probably miss a third or quarter of the drownings. And some that are recorded as RIPS might not be RIPS too. That happens sometimes. So I don't have a lot of faith in the drowning numbers, but I agree. It's again, this confluence of the hazard with people. So it could be a lower percentage. I'm sure there's more people at the beach than ever before, I would think. So it's possible that they've relatively gone down, but I don't know. It'd be interesting to look at.
With more people, you might think that there's more people around the same point.
Yeah, potentially.
And so maybe there's a number that balances out.
And then, the other part is too, at a lifeguarded beach, it's like you have an infinitesimally small, it's like 1 in some number of millions chance of drowning. So if there are more lifeguarded beaches and lifeguards on duty when people are swimming, that's going to reduce the number of drownings too. So it's this confluence of a bunch of different things. It'd be interesting to look at like one location over time and really study how things change depending on the conditions and whatnot. But it's certainly a challenge. Yeah.
It's sort of a follow-up on that. When you do the model improvement, there are severe consequences that are very different from over forecasting or under forecasting. You over forecast and people will stay away from the beach, which has economic impact. You under forecast and people are going to drown, which has different consequences. As you do model improvement or communication of model results, do you consider that sort of social impact?
Yes, that has come up. I would say in discussion, especially with some lifeguards, their concern is, well, what if people really trust the model and you say there's no RIPS and there is, you get it wrong, right? And people said, well, the model said I'm safe, so I could go in. So I think that's a messaging challenge, right? Like when we're giving the model information to make sure people understand what we're saying and what the potential risks still are. But I think that's a great point. I mean, we don't want to, if we forecast hazardous RIPS every day, then your model loses all value because then it says it every day. Right, exactly. So that is definitely a challenge. And we've struggled with that so far just in going in different locations because we know that people in Southern California don't see the ocean the same way as people on the East Coast. Like they see bigger waves all the time there than what we see here. And so you're dealing with different populations who have different ability levels, so there's a lot of differences depending on where you go in the US. And then on the East Coast, you have people, in the Northeast are going to the beach 1 month out of the year, and there's hardly any beach season. And so, in the Great Lakes is like that too. And so there's definitely differences depending on where you are. And so the RIPS could be the same, but should you be forecasting them the same in different places? Because people perceive it differently. So yeah, there's a whole lot of questions there around exactly how you issue the forecast. But again, it gets to balancing. You definitely don't want to be saying something's hazardous all the time, and you don't want to miss hazardous cases. So yeah, that's been a challenge. It's something we're working on. That's a great question.
I just forgot my question. I had a bunch actually, maybe that's why. One was maybe a comment, and that is that like when you showed the photograph of the rip current, there were people were clicking like where's safe to swim, and that wasn't like immediately obvious to me, the differences between those. But I don't find the graphic, the new revised graphic is totally better than the old one, but I find it not as clear, like, and maybe because part of the wave action is covered by text, but it doesn't actually say on there any place what explicit conditions you should be looking for in text. Like it says, it sort of shows it graphically, but it's not immediate. I don't know. It just doesn't stand out to me. The other comment or question I had is, I don't think I've ever gone to a web page to check the status of rip currents before going to the beach. And so I'm curious, like, how do those forecasts get reported to places where people actually go?
That's a good question. So right now, I'd say most people probably get their information through like either local news or the Weather Channel or something like that, right? So they're looking at the weather for the beach, and that's an opportunity for them to hear about potential beach hazards. And I know a lot of the local news stations along the coast and the Weather Channel and some of the other national outlets provide that information pretty regularly in the summertime. We've actually done a lot of work with Weather Channel in particular on getting their information correct. And so they repeat what the forecasts are right now. The problem is that it's usually just like, hey, tomorrow there's going to be an elevated risk or something. So for the entire coastline. So it's very general. And what we'd like to, I think, get to a point is where our model output is available. And then these other, media groups can bring it in and show the time series variability, the variability in location, and be able to say, hey, at this beach at 2:00, it's going to be particularly hazardous, whereas you might go earlier in the day and the tide's high and there's no rips. So I think we recognize that a lot of people don't go to the weather forecast office's web pages. And so it's getting it out to those other intermediate user groups to then communicate that to the public. So yeah, sure.
Would it be possible for places where there maybe are lifeguards that lots of people go to make the forecasts hyper local, like to mark places on the beach where persistent rip currents have been observed, so that so like when you're there, you're like, okay, don't swim there, but go swim here, kind of.
Yeah. So our forecast model cannot do that because it's really, again, the resolution is about 1 kilometer, right? So we can't get down to focusing on specific locations. However, some lifeguard groups actually do that. So like in Kill Devil Hills, for instance, they go out and they will mark the rips with flags. Now, incidentally, people will still go swim there, even with the flags. So it doesn't always work, but some places do that. And I'm assuming it works. I've seen some places in New Jersey, I think, do that as well. So that's something lifeguard groups are starting to do more of. But yeah, I agree. And they often, a lot of times in some of these places in the summer, especially, the rips will be in almost the same place every day. It doesn't move that quickly unless you have a big storm come through or something, but yeah.
So it seemed like when you guys use your prediction algorithm at a different beach outside of North Carolina, you had to recalibrate it. I'm wondering what that recalibration entails and what the feasibility of doing that at all these different locations is.
Yeah, so it's really just refitting the statistical model given the new inputs and the yes/no, whether I see a hazardous rip or not. And so we use lifeguard obs, again, twice a day, so like morning and afternoon. And what the lifeguards will do at all these different beaches, what we like to have them do is say if they observe a rip, 0, 1, 2, 3. So based on the scale of how hazardous they think it's going to be to people, where 0, I don't see any rip, 1, maybe I see something, I don't think it's hazardous, 2, it's like likely hazardous, and 3 is I'm not going to let people go in the water kind of thing. And so what we found is that's really helpful because in some places we see that lifeguards tend to skew one way or the other in terms of what they're saying they see. And so it gives us a way to set that threshold differently. So we can set it where it's 0 and is no, and then 1, 2, and 3 is yes. And so then that's our binary validation data. Or we can do 0 and 1, and then 2 and 3 is usually the 2 ways we break it down. And then what we do is basically you just fit the model to the new data where you have wave height, water level, all those values, and then 0, 1. And then you have that in time, you do the new model fit, and you get new coefficients for all those different input values, and then you can generate new predictions from those new coefficients. So it's actually a pretty easy process in terms of actually retraining the model. It's pretty, I won't say it's trivial, but it's not that hard. The hard part is getting good validation data. So that's been the limiting factor. And then again, it's very specific to a location, and then there's the bias part of what lifeguards are seeing and what they're not seeing. And so that's where I think, we start getting cameras everywhere, and if we have a reliable way to say, yes, no, we see a rip or not, I think that'll make it much easier to calibrate it more broadly. Because again, the actual calibration itself is not that hard. It's just what the data that goes into it is the challenge.
So I was thinking about your nearshore wave prediction model. So these are forecasts by NWS for 5-meter contours.
Mhm.
And are those driven by larger scale models? You tie those into WAM models or other forecasting models?
Wave Watch 3, and then it's Swan for the near shore.
Up
Yeah.
to 5 meters water depth,
Yeah.
and those are locally run. Do you know what resolution those models are run at?
Oh, it's pretty high. I can't remember off the top of my head. Hundreds of meters,
Do
maybe.
they do forecasts for those or nowcasts? Or,
Yeah. Nowcast forecasts up to six days.
And the WFOs that you have up there, is there one from, I can't remember what Maine, the weather office in Gray, Maine, is that one?
Boston, probably.
Out of Boston?
Yeah. And so they've been involved. But the problem with Boston was again, lifeguard data. We have some out on the Cape, I think, but very few lifeguard observations. And so then the problem is like, if we don't have many lifeguard obs and we see an issue with the bias or skill, do you recalibrate off of a few? When we know we created the initial model off a really great data set, how much data do you need to be like, okay, I feel good about recalibrating it for this location, and that you're not going to make it worse by calibrating it to small amounts of data. So that's a challenge, especially again with northern climates, especially just because there's not a lot of beach season, not a lot of lifeguards. But
So this one should be pretty easy. But, so there's a correlation between high and low tides and the likelihood of rip currents. Is there also, I was looking at the table, not the table, the video you had in Miami with the little graph going underneath it. And it was moving pretty fast. I couldn't catch the dates, but is there a correlation between like spring and neap tides and the likelihood of currents?
yeah, potentially. So when you have spring tides, you have a greater tidal range, and so you have lower low tides typically. And so, yeah, so you'll see some differences there just due to the fact that your tides will be a little bit lower. The bigger issue I've seen is like, especially in North Carolina, for instance, it's not a huge tide range there, but during spring tides, over the course of a day, you get a pretty big change in terms of low tide to high tide. And so you could show up at the beach in the morning and it's high tide and there's no rips, and then if you're at a spring tide, that tide changes by a couple meters, maybe 6 feet or something. And then all of a sudden you have crazy rips in the afternoon. And so, people don't reevaluate what they see when they go. They're there and they're like, oh, it's fine. And then, you might get caught off guard. All of a sudden you have strong rips. And that can happen with some of the lifeguard groups as well, I think, is where they'll be really quiet in the morning and then the conditions change or the tide changes. And then you have really a lot of problems in the afternoon. But yeah, so it can definitely vary depending on where you are in the tidal cycle, for sure. Yeah.
Any last questions? Cool. So let's thank our speaker.
Thank you.